Hello everyone and welcome back to another video. In this video we'll be going over problem 16 to 25 on the F equals MA 2021 exam. So let's get started. For problem 16, we have a particle begins at point x equals 0 and moves along the x-axis with some initial rightward velocity v0. And then we're given that it reaches point x equals L and that it has a velocity versus distance graph shown below. So this is its velocity versus distance graph. As you can see, it's linear and it starts at V0 and it goes all the way to L. So we want to see which of these three statements are true. So for one, the particle instantaneously stops at x equals 1. This is true because at x equals L, the velocity is 0, so it must instantaneously stop at x equals L. So 1 is true. 2, the particle could be uniformly accelerated. And to see if this is true, we have to rewrite acceleration as something else. So we know acceleration is delta v over delta t. Or in calculus, you can just replace the delta with the derivative. So this can be rewritten as delta v over delta x times delta x over delta t. And this is because the delta x's cancel out and we're left with delta v over delta t. And delta x over delta t is just the instantaneous velocity. So we can rewrite acceleration as v times delta v over delta x. As we can see in the graph, delta v over delta x is just the slope, and the slope is constant. So the acceleration is going to be some constant times v. But v keeps changing because it keeps decreasing. So the acceleration is not uniform, it goes down. So 2 is wrong. For 3, the particle could be performing simple harmonic motion. And for this, we can look at how the position versus time graphs and the velocity versus time graphs for a particle in simple harmonic motion. The position versus time will be x equals a times cosine of omega t, and the velocity is going to be negative omega a sine of omega t. And the relationship between x and v is not linear, so it could not produce this type of graph. And this means that the third statement is also wrong. The correct answer will be A, only 1. Problem 17, we have that the shorthand of a clock is exactly half as long as the longhand and rotates twice for each rotation of the longhand. If we take a look at this clock right here, we see that there's 2 points A and B on the longhand and 1 point C on the shorthand. And it's going to rotate with angular velocity 2 omega, and the longhand will be rotating with the velocity omega. And let's say that the distance from the center to C is d, then the distance between center and B is also d, but the distance between the center and A is going to be 2d. And we want to compare the accelerations at points A, B, and C. Okay, for this we can just use the fact that the centripetal acceleration A sub c is going to be equal to v squared or omega squared r. And we just plug in to the omega and the distance into this equation and see what we get. For c, we get it's equal to 4 omega squared d. For A, we get it's equal to 2 omega squared d. And for B, we get that it's equal to just omega squared d. So B is the lowest, then A, then C. Answer truest that works is C. Problem 18, we have a factory that's producing some smoke, and the smoke rises constant speed relative to the air around it. We know that the air is initially still, but then starts blowing to the right and then becomes still again. We want to find the shape of the smoke. So let's draw the factory first. This is the thing that's emitting the smoke. So at the beginning, it's going to be just a straight line because the air is still, so it's not going to be pushing the smoke. And then once the air starts moving, all of this right here just gets pushed to the right. So it gets pushed to the right around here, and the new stuff that's being created is going to create a diagonal line. And after when the wind stops, it's going to create this huge diagonal line and some straight part. And then it will become still. So it's just going to have another constant area again. So it's going to be constant, then a diagonal, and then constant again. And the only one that shows that graph is B. Problem 19, we have a spherical planet with uniform mass density with mass m and radius r. Cavity r/2 is dug out, and we want to find the gravitational field at point P. And this is the diagram right here. So we have the center here, point P here, and the center of the whole planet right here. The way we can do this is by using the fact that we can superpose the gravitational field. And what this means is we can find the gravitational field of the whole sphere and subtract it from the gravitational field of this hole. And we must do this vectorially because the gravitational field is a vector, so we can't just subtract the magnitudes. Okay, so let's try finding the gravitational field of the whole sphere first, of the original planet without the hole. You know that it's given by gm over r squared. This is the gravitational field of any object, where m is the mass of the object and r is the distance from the point to the center of mass. In this case, the distance from point P to the center of mass is r, and the mass is m, so it's just going to be gm over r squared. And it's going to point downwards like this towards the center. So it's going to be negative in the y hat direction. If we assume that y hat is going upwards and x hat is going to the right. And for the hole, it's going to be the same thing, except it's going to point this way. And the new mass is going to be m over 8. Because when you half the radius, you divide the volume by an 8, meaning that the mass is also divided by an 8, because there's uniform mass distribution. And the distance between point P and this center right here is r/2 and r like this. We can use the Pythagorean theorem to find the distance. And if you do that, we get 5r squared over 4. Take the square root of that. And now we can plug this value into the equation. And if you do that, we get the total gravitational field is gm over 8 over 5r squared over 4. This is equal to gm over 10r squared. But we have to split this into components. And we know that if we multiply this by r/2 times the hypotenuse, which is just sine of theta, then we get the horizontal component. So the horizontal component is going to be gm over 10r squared times 1/2 over root 5 over 2, which is just gm over 10 root 5 r squared. And then the vertical component, you're just multiplying by 1 over root 5 over 2. So it's just going to give you gm over 5 root 5 r squared. And this is also going to be pointing downwards and pointing to the right. So it's going to be positive in the x hat and negative in the y hat. Now we can subtract these two gravitational fields. And if we do that, we get some really messy equation like let's just take out all the gm over r squared. So we get something like -1 plus 1 over 5 root 5 whole thing squared plus 1 over 10 root 5 whole thing squared. And if we simplify this out, we get that this is equal to 0.912 if we simplify this square root. For problem 20, we have something called the terminator, which is the line between day and night on a planet or moon. And we want to find how fast it moves across the surface of the equator on Earth's moon. We're also given the radius of the moon. We know that one whole rotation about the x-axis of the planet, the terminator will travel 2 pi r in a time of one rotation. And this one rotation is basically just 1 day. But 1 day on the moon is not 1 day on Earth. It's going to be actually around 1 month, which is around exactly 28 days. So it's going to be 28 days. And now we can just plug in r into this equation right here, and we can solve for the velocity. So this is our velocity. It's just distance over time. And if we simplify this, we get that it's equal to 4.5 meters per second. For problem 21, we have a solid sphere at the top of a ramp of height h, inclined at an angle theta. We have that the static and kinetic coefficients are 0.2 and it's released from the top of the incline at rest. We want to find for what values of theta is the total kinetic energy of the system greatest. So this is just conservation of energy, and it's basically asking for what value of theta will no energy be lost to friction. So for what value of theta will it roll without slipping? And we can find this value of theta by just finding the forces on the ball. So if we draw our inclined plane at our ball, this is angle of theta, we know that the moment of inertia of the ball is going to be 2/5 mr squared, where m is the mass of the ball and r is the radius of the ball. And the only force that is rotating the ball is going to be friction, which we can just call F. This. So our friction is going to be equal to I times alpha. Well, friction times the radius because it gives torque. So this is our torque and this is equal to I times alpha. And since we don't want it to roll without slipping, alpha is just going to be A over R. Okay, so if we plug these values of I and alpha into the equation, we get that the force of friction is going to be equal to 2/5 times m times a, where a is the acceleration of the sphere. And then we can look at the forces on the ball that's causing it to accelerate. And we're going to have two forces, mg times sine theta, which is the parallel component of the gravity of the ball to the ramp, minus the force of friction pushing it backwards, so minus F. This is going to be equal to ma. Okay, now we can plug in this value of F into the equation, and if we do that, we get that g sine theta is equal to 7/5 a. And if we solve for a, we get that a is going to be equal to 5g sine theta over 7. Okay, well this doesn't really help much, but we can use the fact that at the maximum theta, F is going to be equal to mg cosine theta because this is the maximum value of friction. Otherwise it will start slipping and causing us to lose our kinetic energy. This is our maximum value. And now we already solve for A, so we can just plug in F into this equation and A into this equation, and we can solve for theta. If we do this, we get that g cosine theta equals 2/5 times 5g sine theta over 7. And then we can just do some simplification. And if you do that, we get tan theta is equal to 2/7, or the maximum value of theta is equal to the arctan of 2/7. And if we plug this into the calculator, we get this is approximately equal to 16 degrees. So we want to find for what theta, values of theta are less than 16 degrees. And the only value of theta that's less than 16 degrees, that is one of the answer choices, is just 10 degrees. So our answer is A. For problem 22, we have a ship is going into some hunk of ice and it wants to push the ice underneath the ship. We have that the coefficient of static friction between the ice and the ship is mu s, and we want to find for what theta will the icebreaker function as intended. And we can just use a simple formula that says that if we have a block on a ramp with coefficient of friction mu s and angle theta, we get that the minimum value of theta needed to push the block down or allow the block to fall down is theta is equal to the arctan of mu. And the same exact principle applies here because we can imagine this ship as the block and this ice as the ramp or vice versa. So we know that we must have a tan or a cotangent in our answer. So we can cross out D and B. And then we can just look at which sign makes sense. We want the mu sub s to be as small as possible, right? So we want cotangent of theta to be greater than mu s because we want mu s to be small. And if it's greater than, if it overcomes mu s, then it's able to slip. For C, if mu sub s is greater than, then it won't be able to slip. It will just get stuck and won't be able to push it down. So our answer is A. For problem 23, we have an imperfect spring with a restoring force F that depends on the displacement x, and is shown as the graph over here, F and x. We're given that the slope of the curve between this point right here and this right here is negative k, and this to this is also negative k. We have a mass is attached to the spring and released at position x equals a, so probably somewhere over here, a and negative a. And we want to find the period of the subsequent motion. So we can split this into two different parts, the diagonal parts and the straight part. Let's start out with the diagonal parts. So if we look closely, this diagonal part just closely represents the normal F versus X graph of a spring going under simple harmonic motion. It's going to be something like this. And this is exactly what we see, where the slope is negative k. So this is just going to be the normal 2 pi square root m over k, because that's the period of a spring going under simple harmonic motion. Okay, so that takes care of the diagonal parts. For the straight part, it's just going to be the time it takes for it to travel across this is going to be d over the velocity. But in this case, it's going to be traveling once and then it's going to be coming back. So it's going to be 2 times the distance, which is 2d. So it's going to be 4 times d over v. And we can find v using conservation of energy. We know that 1/2 mv squared, or the kinetic energy at this point right here, is going to be the potential energy from x equals a to x equals d, or 1/2 k times a minus d squared. And we can solve for v. If we do that, we get v is going to be equal to a minus d times the square root of k over m. Cool. Now we can plug this value of v into t, and this gives us 4d over a minus d times square root of m over k. And now we can add this period to the straight part, diagonal part to the straight part. And if we do that, we get the answer as C, or t is equal to the square root of m over k times 2 pi plus 4d over a minus d. For problem 24, we have 2 satellites that are in circular orbit around a star with radius r, speed v, and period t. And they're initially diametrically opposite from each other. So we have one satellite over here, let's call this satellite A, and another satellite on the opposite side, which is satellite B. And they're rotating in a path like this, so a circular path. And then we want satellite A to meet satellite B in time t over 2, and we want to find for what speed will this new satellite reach the other satellite. So in time t over 2, satellite B will reach where satellite A is currently located, because the whole period is t, so t over 2 means that you travel half of the path. And this means that if after time t over 2, you want to go back to the position where A was located. So this means that that A must decrease its velocity such that it has a new period of t over 2. So this is going to be its new period in order for it to reach where it is right now after time t over 2. Now we can use Kepler's third law, which says that t squared is proportional to a cubed. And this means that t1 squared over a1 cubed equals t2 squared over a2 cubed. And now we can find the new semi-major axis of the second satellite in time when it has a period of t over 2. So we just have to plug in t over 2 as t2 and solve for a2, where a1 is just going to be r because that's its semi-major axis. So when we solve for a2, we get, and then after getting this equation, we can just move a2 to the other side, and then we get that a2 is going to be equal to r times the cube root of 1 over 4. So this is the new semi-major axis of the first satellite. Okay, so now we can find for what new velocity will our satellite have this semi-major axis. And we can do this by using the theorem that states that the energy of a satellite in orbit is going to be negative g m m over 2 times the semi-major axis. And this is just the same thing as the negative of the kinetic energy of the object. So this means that the change in energy is going to be negative gm times m times 1 over 2 r minus 1 over 2 times the new semi-major axis. And this must be equal to the negative of 1/2 times the mass of the satellite times its original velocity squared minus 1/2 times the mass of the satellite times its final velocity squared. Now we can cancel out the masses on both sides, and we can solve for VF by plugging in A2 as this new semi-major axis. Okay, so first we can get rid of this minus sign on both sides, and if we simplify, we get g times m over 2 times 1 over r minus 1 over r times the cube root of 1/4, but we can just move that to the numerator, so times the cube root of 4. Then we can bring the r to the outside, so we're just left with 1 minus the cube root of 4. This is going to be equal to 1/2 v squared minus vf squared. Okay, now we can get rid of this 2 and this 2. And one more thing we need to do before we can finish is that we know that using centripetal acceleration, we know v squared over r is going to be equal to gm over r squared. So this means that v is going to be equal to square root gm over r. This means that gm over r is the same thing as v squared, and therefore we can get rid of this, place that with the v squared. So after getting this equation, we can move the v squared to the other side, which gives us v squared times the 2 minus the cube root of 4, which is equal to the negative of vf squared. And this means that vf is going to be equal to v times the square root of this quantity in the middle, which is 2 minus the cube root of 4. And evaluating square root of 2 minus the cube root of 4, we get approximately 0.64. So VF is 0.64 times V. And this means our answer is B. For the last question, we have some guy who has a sprayer that's at rest at a distance of 8 from the center of some planet orb, which has a radius of r. And it ejects a bunch of pellets radially outwards, and they're launched in all directions with the same speed v, so that a planet launched directly away from orb can barely escape it. We want to find what fraction of pellets eventually land on orb. Okay, so the first thing we can do is we can find the velocity at which they are being launched away. And we can do this by using the fact that the escape velocity is equal to the square root of 2gm over r. But in this case, r is going to be h because we're shooting them at a height of h. Okay, so now we know the velocity at which they're being shot at. And the pellets that will eventually reach the Earth will travel a specific orbit. So let's say that it's launched at some velocity v with angle theta. Then those that will eventually reach Earth will follow a path, or not Earth, the planet orb will follow a path that hits right here. So any pellet that's being shot will follow some path like this, or follow some path like this on the other side. So any angle that the pellet is being shot at and follows this path, any angle between this and 0 will land on orb. So we need to find for what angle theta will the pellet will basically like become tangent to the planet at this point right here. So it's going to be a distance r from the center and a height h. And there's multiple ways we can do this. The first way that I can think of is by using conservation of angular momentum and conservation of energy. So let's say that it's being shot out at velocity v at angle theta, and it reaches a distance r from the center of the planet. Then from conservation of angular momentum tells us that v times sine of theta times the distance from this point to the center of the planet, which is h, times the mass, is going to be equal to m times this new velocity, so v sub n times r. We can get rid of the m's. Okay, so now that we have our angular momentum equation, we can easily find Vn as well, because at the point where the pellet reaches the planet orb, it's actually going to be traveling at the escape velocity, because the path that it takes, if it keeps going on that path, it will eventually escape the gravitational pull of the planet. So V sub n right here is just going to be square root 2 gm over r. And now we can plug this value of v into the equation, this value of v sub n into the equation, and if we do this, we get that sine of theta times the square root of 2gm over h times h is equal to square root of 2gm over r times r. If we simplify a bit, we get sine of theta times the square root of h is equal to square root of r. And now we can use the hint that they gave us, that sine theta is approximately theta, because theta is very small. So if we replace sine theta with theta, we get theta is equal to square root r over h. So this means that this angle right here, from the velocity to the vertical, is square root r over h. This means that the range of angles that will eventually reach the Earth planet orb is going to be 2 times theta, which is 2 times the square root of r over h. And we want to find what fraction of pellets eventually land on orb. So we want to find this theta all over the total degree in radians, which is 2 pi. And if we simplify, we get 1 over pi times square root of r over h, which is e. So our answer is e. Okay, so that's it for today's video. Thank you guys for watching. And I'll see you guys later.